In this demo, we are going to revisit the ring modulator circuit from the frequency domain simulation section. This time, we are going to run a time domain simulation using the transient sample mode. To do so, we need to edit the element properties. First, click on the ONA, scroll down to the Numerical Properties, and set the analysis type to impulse response. We are going to run a TE simulation, so let's set the orthogonal identifier to 1. Now let's update the numerical properties of the waveguides. Use the mouse to select both of the waveguides. Scroll down to the numerical properties. The group delay is critical for the waveguides, so we will set the digital filter to true, the single tap filter to false, and the number of taps estimation to group delay. The total delay compensation required is 5, as there are 5 connections along the ring. For straight waveguide 1, set the delay compensation to 2, and for waveguide 2, set the delay compensation to 3. Now use the mouse to select both waveguide coupler 1 and 2. We are going to treat these as point couplers with no delay. To do so, we set the number of FIR taps to 1. Let's use a DC source amplitude of 0. The last thing we need to do is set the sample rate. Click on the ONA and recall that the frequency range currently inherits the root element sample rate. We will use the script prompt to calculate the minimum sample rate based on the recommendations in the last unit, then update the sample rate. The minimum sample rate is the delay compensation 3 times the speed of light c divided by the group index, which is 3.9 for the TE mode, times pi times r, where r is 40 microns. Here 3 is the larger of the two delay compensations. The question mark is used to display the result. The minimum sample rate is 1.83 times 10 to the 12. Click outside of the circuit to get the root element properties. We'll set the sample rate to 2 times 10 to the 12. Press Run. The simulation completed successfully. Now let's set the sample rate to 1 times 10 to the 12, which is below the minimum value. Run the simulation. We see that we get a warning message that says to increase the sample rate to 2 times 10 to the 12. Let's return it back to 2 times 10 to the 12 and run. We are now going to compare the free spectral range value to the value predicted analytically, which is the speed of light c divided by the group index 3.9 times the total ring length 2 times pi times r, where r is 40 microns. The free spectral range is predicted to be 0.306 terahertz. Before we look at the simulated free spectral range, let's first plot the transmission for the drop channel, input 2, to make sure we've captured multiple peaks in our simulation. Set the transmission to the absolute value squared. Now that we know we've captured multiple peaks, let's plot the free spectral range. It is close to the expected value of 3.06 times 10 to the 11 Hertz. Now let's set the delay compensation of the waveguides to 0, and we'll rerun the simulation. When we plot the free spectral range, we see that it drops to around 1.7 times 10 to the 11 Hertz, which is incorrect.